lecture today will be on the exchange between biometrics and forensics. So how to use biometrics in forensics examination. So let's bring the floor.
Okay, thank you for your introduction. Thanks again for inviting me here. So the two, if you think about how biometrics, where biometrics is applied, then I find two areas actually. One is identity and access management, is always related to things like access control and who are you and what are your rights. And the other big domain is law enforcement. And there is a bit of overlap between the two, but I think I could separate all the, I could categorize all the applications of biometrics in either identity and access management or in law enforcement. So law enforcement is forensics more or less. So today the topic will be about biometrics applied in forensics, and there will be two parts. One is about, both are about face recognition. One is more to assist the forensic examiner comparing faces, and the other one is more about face recognition at very low resolutions. So the first part is how pattern recognition, say biometric pattern recognition, can support the forensic examiner. And then let's go to the very beginning. If we look at the question that biometrics usually tries to answer, is what we see on the right hand side. Are these two images from the same person? Actually, a forensic examiner, so in access control we have this question: if you produce your passport at an e-gate, your image on the passport is compared to a live scan, and the system is deciding whether this is you or not. A forensic examiner, you may recognize these two suspects over here, but the forensic examiner basically does the same thing. He has an image taken from a crime scene, and he has an image taken from a suspect, and the question is, are these images from the same person? So this is what is the same. The answers could be a bit different. So for instance, in the biometric system on the right hand side, what we do is we compute some score, some similarity score of images X and Y, and if it's above a threshold, we decide, yes, these images are from the same person. The forensic examiner will, in his report, write something. He has a hypothesis. The hypothesis is these images are from the same person, and what he is quantifying in a, well, not really quantifying, what he is trying to express is whether this is hypothesis is supported or not. And this is usually in categories running from no support to very strong support. So this is very qualitative, categorical. So the questions are the same, the answers could be slightly different. Also the methods are different. The right hand side is a standard nowadays in times of deep learning, a little bit old fashioned, but it's a standard way of face recognition. Actually, one of the more popular systems, traditional systems, work with a variant of elastic bunch graph matching, where you put a network on a facial image and you compare node by node until you to express similarity. But what a forensic examiner traditionally does is he looks at shapes and characteristic features. So we see size of ears, profile, shape of ears, and maybe looking at facial marks. So this is the kind of comparison that a forensic examiner would do. Also, the material that the biometric system and the forensic examiner are looking at is a bit different. This could be input to a biometric system, but this is usually where the forensic examiner is looking at, so very low quality images. So what is the purpose of this research? Well, the forensic examiner is actually the weak link in the chain. If he has been examining images all day, he may be tired. He may overlook certain things. He may also be biased to a certain extent. He should not be, because what we want is that the forensic examiner is not like the police. The police is willing to catch a suspect and to find a criminal and to get the criminal convicted. The forensic examiner is actually the person who should make a kind of objective statement. But he's human, or she is human. So humans can make mistakes. So if we would automate part of the work of the forensic examiner, his task would become easier, the result could be more objective, And another question is, what we learn here, can we also apply that in standard face recognition? And what we will consider here is the example case of facial marks. So recognition of faces based on facial marks. And this has been reported in the TIFFs actually 1 year ago. So what are facial marks? This is the 19th century impression of facial marks. And on top you see typical examples. So they have several appearances: moles, pockmarks, raised skin, scars, to name a few of them. And the method that we propose is actually a very simple one. We will start by looking at frontal images for the moment to make the comparison, and we will overlay a grid on the image. So this is still where the forensic examiner, well, we could do two things here. Either the forensic examiner could mark the facial marks on the grid, or we could have an automated detection method that actually per cell tells us whether there's a facial mark or not. So we'll start off with the with the manual approach, but the automated one, we investigated that as well based on deep learning, and actually that works quite well. So, and then we'll automatically compare the annotated grids. So the grids could be filled manually, but then we will make the comparison automated. And we'll distinguish 3 types of features. The first one is binary. It's a very easy one. There's either a facial mark in a cell, 1 or more, or none. So this is a binary one. 0 for none, 1 for any number of facial marks. To make it a little bit more exclusive, we can define categories. Either 0, 1, 2 or 3, 4 or more. So we have a 4-category model. And the last one is simply putting the number of facial marks in the cell. So it's getting more and more refined. And one problem that you will have to solve is, what grid size do we take, and how do we standardize the grid size? Well, we use interpupillary distance, so the distance between the pupils of the eyes, the centers of the eyes, and we express the square grids, and we express it into interpupillary distance. So it could be 10% interpupillary distance up to maybe 50%. Then this Chris Zijnstra, who was my PhD student, has annotated a large part of the, and he used his family to assist him there, but a large part on the of the FIGC version 2 dataset on this grid. So those are all neat frontal images. And if you plot all like a probability density function, the scatter plot of the facial mark, this is what you would get. So one observation is that actually these are not uniformly spread over the face, but there are certain regions like the cheeks that have clearly more facial marks, and the forehead clearly has fewer. Then we took 2 examples of images. B and C are of the same person. This is what we have in the training set, just a single image with a number of facial marks. And another another one used for testing of the same individual. You see similarities but also differences. So facial marks are not really constant. And D and E are similar, a different individual. And you see that if you take different observations, you have different sets of facial marks. So, how do we classify these 2 images? What kind of comparison do we do? And then I come back to the story of last Tuesday. We like to work with likelihood ratios. Actually here, this is very interesting in a forensic case because the likelihood ratio can be used to quantify evidence. And you can easily see this. This is the Bayesian equation, and this part is the likelihood ratio. So xi is the ith cell of individual x, yi is the ith cell of individual y, and the probability when they're from this, under the condition that they're from the same individual of this cell is pxy. So this is the likelihood ratio, and this is this probability if they're different. And these probabilities we can actually just estimate from a training set. Now this is the prior odds. So this is the probability without knowing anything, we may have an impression whether the subject actually, the suspect actually is the perpetrator. For instance, if we were working in a building, we have 10 people working in this building, then it's a probability of 1 in 10 that this person actually is the perpetrator. So you may have an idea about the prior odds. The posterior odds are the probabilities once we've seen the observations. And what the likelihood ratio does is amplifies or weakens the prior odds. So this is when you know nothing, and this is the probability ratio when you've seen the evidence. So this is an objective number that can help a judge make a decision, which is much sharper in a sense and much better formulated than support or no support for a hypothesis. So that's why we make it objective. And as I explained last time, this is also will lead us to optimal classifiers, which is also a good property. So this is the likelihood ratio is the thing that we want to compute. And actually, if we assume the cells to be independent, then these probabilities split up into products, and we can measure the probability per cell. And actually, that's pretty easy because we have a lot of training data. And again, the training data does never contain the same individuals as the test. So training data is always separate. It should be data representative for the group of people that we're looking at. So if we know that the suspect is a white male, then probably we could train the whole system on white males. If we don't know anything, we have to take a broad population. So you can build in the things you know in training, but never on the same individuals. So these probabilities must be estimated from training data, which is pretty easy. For instance, if you want to have for the binary case, we have in one certain cell, no marks, no marks, no marks, 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 no marks, and marks, marks. And we hope that, for instance, if we're dealing with the suspect, when the suspect is the perpetrator, then this one should be higher than the other two. So these, by counting, we can estimate those probabilities. So then we distinguish two cases. If we don't have a lot of data from a suspect or from a perpetrator, so not much trace data, we can work subject independent. We simply count the statistics for everyone. If we have enough data on a certain suspect, then we can make it suspect dependent, and we can express the probabilities for a specific suspect. That will always lead to better decisions. So that the question is this specific person, or is it a general one from a general distribution? So these two cases will lead to different results, but we can discriminate between both. So, how will we do our evaluation? Well, you see a table over here, and there's features, and features are either untrained. So I said if you want to apply this likelihood ratio framework, we need to train, but we can also use an untrained classifier if you want. And then, for instance, for the binary case, we can use a Hamming distance, and if we take numbers, we can take a chi-square distance. If you go for a trained classifier, then in all cases we can train a likelihood ratio classifier. So we're not covering all the cells. We worked on FIGC data, and we had 568 subjects. Well, to split them for the training, we took the subject with fewer than 25 images per subject, and this was our general training data set. And for the subject specific, we took the first 10 images of the remaining 192, and we're testing on all the other images. Details you can find in this publication. So, let's see. In order to express how well this works, we're not presenting likelihood ratios. We're using the likelihood ratio as a kind of score, but we're looking at equal error rates. And the first thing is that we had this cell size. So we can vary the cell size and see how well the system works. And we start from, this is the fraction of the interpupillar distance. So this is 5% fraction, and this is an entire pupillar distance, and we're moving in steps of 5%. And you see a few of the classifiers pointed out here. The first one is the Hamming distance, and the Hamming distance seems to improve when we make the interpupillar distance larger. But basically we're actually counting the number. In this case we're simply counting the number of facial marks in the face anyway. Let's see whether they come to the same conclusion. If we look at the subjects, at the general one we get the green line, so we see that if we increase the grid side, at first we see an improvement, the equal error rate goes down, and at a later stage it goes up again. And we see the same behavior for the subject-specific one, but what we see here is that actually the subject-specific one is slightly better. So this is binary and Hamming distance, and the other one is categorical and chi-square, and we see actually chi-square behaves similar as Hamming distance, higher error rates, but if you look at the two categorical classifiers, we see that there is a kind of optimum for a certain, it's not very critical, there is a kind of optimum for the interpupillar distance. And we can, of course, if we take a small interpupillar distance, then it may be that sometimes a facial mark is in one cell, sometimes it's in the neighboring cell, so this is creating some noise. But if we make it larger, we use specificity of the measure, so there must be an optimum in between. And we see that actually we get quite decent equal error rates, especially for the subject-specific case. If you would be interested in ROCs, then I've plotted those over here, and we did those for more or less the optimum cell size, which was somewhere in the middle, so 0.5 interpupillar distance. It actually means that we don't have too many cells in the face. And here we see the ROCs, the binary case on the left-hand side. Hamming distance is performing quite poorly, but we see that the binary ones are doing a reasonable job, and especially at a certain point, the subject-specific one becomes the better one. If we look at the more elaborate cases of the categorical ones and the chi-square, we see somewhat better behavior, and actually always that the subject-specific method benefits from that. So, the question is, how well does subject-specific recognition actually work? Is this interesting? And in order to show that, we have looked at the cases where we get perfect separation. Perfect separation means equal error rate equal to 0. And then we see that in this case with the diamonds, which is the categorical subject-specific one, we see that in quite a few cases, almost 20% of the data, we have equal error rate 0. So that means that for these cases, we have actually perfect separation for 20% of the images. And for all the others, it is less. Usually in biometrics, we don't do subject-specific from the eyebrows. For instance, the angle of the eye is a point here. It's not the eyebrow, it's the angle of the eye. Then there's eyebrow comparison, different characteristics. There are standardized characteristics for that, A, B, C, D, E. So different things. Here is looking at the mouth, and here is looking at the height of the mouth, the width of the mouth, and the width of the noise. And what we see is 3 lines. The blue line is always the general ROC. If you don't work if you work suspect unspecific. And basically, if we would look with our experience from biometrics at those ROCs, you would say the blue one is actually pretty poor. You would not sell that. The red one is the worst performing suspect. Usually a suspect which has a quite average characteristic, so this one is probably the very characteristic mouth. And you see very characteristic eye angles in the upper left one. But then there are certain suspects which have different characteristics, and they have pretty good recognition performance. So that means that in contrast to what we do in biometric face recognition, in the forensic case, it pays off if you have enough data some suspects have very discriminated features, even when the general biometric performance is poor. So, takeaways of this first part. Well, the likelihood ratio, coming back again, my favorite classifier, helps to quantify evidential value, which is good for the forensic examiner. With proper features, facial marks can be discriminative. We saw that we actually achieved pretty low equal error rates. The trained classifiers, as usually, outperform the untrained ones. And a subject-specific approach can be helpful in forensics. And we have been working further automation is needed. We also now have automatic classifiers for the facial marks, and we can come up to the same performance. So, this is part 1. So, focusing on the forensic examiner, I would like to move on to part 2. There's a number of authors here. There's my colleague Luc, there's PhD student Yushi, and there's my nowadays postdoc, but she used to be a guest 1 year ago dancing. And they all work on, and this is about low resolution face recognition. So, there's a list of things that we will discuss. I won't list them here, I'll just show you. Face recognition at a distance. So low resolution is one way of terming this problem, but it's not really the correct way. Let's talk about face recognition at a distance. And I'll show that images at a distance are low resolution, but there is more going on than just low resolution. So the typical kind of images that we have to deal with are shown in these 2 pictures. This is from a surveillance camera, and this is somewhere from a crowd. And we see that actually if you enlarge these images, you get pretty low resolution faces. So this is mainly forensics. You don't do access control in this way. You simply want to find people that committed the crime, whether someone is present on a video tape or not. So many more challenges, low resolution being one, but also pose elimination, and we'll focus on low resolution here. And so that's why we consider more or less frontal poses. So, this is the biometric comparison story. You know this, there's a reference image, there's a test image. We compute a comparison score and we compare that with a threshold. This is the way the system works. And actually, if we want to express performance, we will do that in terms of an ROC. You've seen that one as well. False match rate, true match rate, and this is actually a pretty good system. Getting, if we look at false match rate of 10 minus 4, for instance, we get something like 99% correct recognition rate, which is pretty good. And this is on realistic data. So, verification, no identification rates, because usually they depend on gallery size, so 99% is for a 10-person gallery is a lot different than for a 1,000-person gallery, so no identification rate. And I think that systems are better compared in terms of verification performance. And anyway, it's more realistic for the case that we're considering. So, faces at a distance. This is my PhD student. She volunteered to record a small data set, and we're just willing to look at what actually is happening if we take a standard camera and we increase the distance. So this is our gallery image, which is, let's say, 50 centimeters or 1 meter away from the camera. And if we increase distance, you see that gradually we're losing detail. You could also see that it's not just losing resolution, but many other things are happening as well. There's geometric distortion, there's noise coming in, there could be atmospheric distortions as well. So if I go to the distance, and if you really want to recognize something like this, it's hard. The interesting part is if you're sitting at the back of the room, probably this one looks better than from front, because if you low pass filter, you kind of get back the original image. If you squeeze your eyes a little, this is also what happens, and it gets a better quality. Okay, but the statement is that faces at the distance are not just low resolution images. That's also illustrated over here. So there's a data set that has this type of images, and these are at the distance. This is the high resolution one, and if you simply downsample the high resolution one to the same resolution as this is what you get. So many people that work on low resolution face recognition actually train and test their systems on this type of data, and they claim good recognition performance. But if we take those systems and we can actually confirm the performance if we take these images, but if we run them on the realistic ones, performance drops drastically. So the problem is much harder than just lowering the resolution. So we see all kinds of things. There's low resolution, there's filtering effects, there's noise, there are compression artifacts, and there is projective distortion. So the state of the art for recognizing this type of images actually is 73% true match rate of 10%. So this is a totally different ballpark than high resolution recognition, where we talk about false match rates of 0.1%. So this is 100 times higher false match rate, and we get true match rates which are even lower than that. Very difficult problem. Illustrated again, this is the high resolution thing that I showed, and we see high recognition rates. These are 3 systems. I'll explain them later, but we see that the ROC is much more away from the upper left corner. Okay, one of the important things is alignment, and it is very interesting to do an experiment there. So these are real commercial systems, and well, let's see. This is an LDA, so this is a high-end commercial system, and this is a simple LDA-like system, the kind of system that I also discussed in my previous presentation. What we did here is we're working with downsampled images, but if you align the image, so you have 2 images, let's say one high resolution, one low resolution. If you obtain the low resolution image by first aligning the high resolution and then downsampling it, is one case. You could also first downsample it, so go to low resolution and then align, and then you lose details and the alignment becomes more difficult. So what we see here in the realistic case, we see this type of performance as a function of resolution. So resolution goes from 131 to 23 pixels image size, pretty small. And the real system, you see the performance in terms of verification rate going down. If I would first align the image and then do the downsampling, actually I don't lose performance. That's weird. And if I do it the other way around, if I first downsample and then I align, I'm pretty close to the realistic system. So the same if I look at a high-end commercial system. If I take the real performance, dropping off quickly, you see actually that the high-end commercial system, which is a license of several thousand euros per year, performs worse on these images than the simple LDA system. It's dropping off quickly. If I first do the downsampling and then the alignment, I get more or less similar behavior, somewhat better because other aspects of the image quality are better. If I first align and then downsample, again, I hardly lose performance apart from at the very end. So one of the real problems we have to deal with is with low resolution images is proper alignment. And that is hard because how do we do alignment? Usually by landmarking. So we kind of manually or automatically detect the centers of the eyes, maybe the mouth, and we align images based on that. If I have 10 pixels between the eyes, or even less, this is a very hard job. So, but we'll have a solution. We'll demonstrate how we can do this. So that here we see 2 basic solutions for the low resolution problem. One is we have a high resolution image, and what we do is we compare in the high resolution domain. So we upsample this one, we take the same feature extraction, and we do the comparison. This is method number 1. Method number 2 is, well, let's downsample both of the images and then do low resolution feature extraction. Method number 3 is why don't we simply accept the fact that we have different types of images. One is high resolution, and we do high resolution feature extraction from the high resolution. This one is a low resolution at a distance. Why don't we extract low resolution features here? And we have a mixed resolution comparison system. Then we're not tweaking the image to either high or low resolution, but we're simply accepting the fact that these are different images and that we have to compare heterogeneous types of features. So this is comparison in the mixed resolution domain. This is what we implemented. I will not go into the details, but you can reformulate the likelihood ratio classifier in these terms. What we see here is basically a projection to a subspace that the methods share, and this is the likelihood ratio classifier in that subspace. It is on the Gaussian assumptions. You can pretty easily derive this, and we published this in IWPF 2015. And what I explained on Tuesday, this is interesting because the likelihood ratio classifier does not only look at differences between the images, but it also rewards the rareness. This is one thing. The other thing is, how do we deal with the alignment if we cannot landmark? Well, what we could do is we could do score-based registration. So we simply start, usually we have something like the Viola-Jones face detector to detect the images. The Viola-Jones face detector will give you a rough indication where you can find the eyes. So we have an initial estimate of eye coordinates in the high resolution image as well as in the low resolution image. What we can do then is we can move around this face a little bit. And basically if I move it, let's say 5 pixels up, 5 pixels to the right, well 3 left, 3 right, so I get 25 options. If my recognition system is fast, I can make all the comparisons and I simply go for the maximum score. In that case, I don't have to do landmarking, but I have a kind of implicit registration. So that is the other thing that we did. Then, how well does this work? Well, one data set that is particularly suited for this is the SC face data set, and we ran our results here. And you see what different conditions. We can train on certain subsets and we can test on other subsets, so we split by apply. It's still recognition performance that is far away from high resolution, but we see a big improvement with respect to the state of the art by having another view on the problem and by better looking at the registration problem. If you publish this, then the reviewer will say, why don't you use deep learning? So papers sometimes get rejected because we don't use deep learning. Sometimes they get rejected because we do use deep learning. Anyway, we cannot avoid using deep learning. So this is the system. So this was the original system that we were working with. Simple, like this is PCA LDA-like, likelihood ratio classifier. And we thought, okay, let's add a deep learning feature extractor. So this is what we did. Over here, there's a CNN for high resolution feature extraction, and we use that in both cases. So we simply use it as a feature extractor. We could easily do this because Dan Zheng, who was our guest in her work in China, developed such a classifier. So she also had her results, which were comparable to our results at first, and what we did is we took her system and we added this comparison system. So this is kind of a Siamese twin network. This is the network as she designed it. It's a number of convolutional layers, and normally it ends with a softmax layer. So what we did at this point is we threw away the softmax layer and we stopped at this point as a feature extractor. Training is an issue. If you want to look at deep networks, you need enough training data. So we did not take, this was a custom designed deep network. So how did she get to a training set? Well, basically what she did is she collected all the possible data sets, put them into one big training set, and then on that trained her network with mixed resolutions. And you see SC face is not part of it, so the training is completely separated again from the testing. Well, this is where we are. two things, verification rates. This column, rank 1 accuracies as well. And what we see is that Dan's work in China brought it to 70% on this data set. Our classifier, the mixed resolution one, previous part of the talk, 73%. The combination is a big jump forward, we go to 84%. Verification rates are also improving, but not as dramatically as the, sorry, identification rates are also improving, but not as dramatically as the verification rate. And then these are the kind of images that we're dealing with, so this is basically almost just pixels. We've made some more steps, but I can just give the numbers from the top of my head. What we did is we started with a pre-trained RLDN, trained on relevant data. We developed a cost function at this point, including this network, had a feedback and a fine-tuning for the last layers here, and then we can go to 90%. So there's still room to gain. Biometric registration is crucial, and is a problem for very low resolution images because we don't have reliable eye coordinates, but the matching score-based registration really helps in this case. Mixed resolution classifiers actually outperform the state of the art, and CNN-based feature extraction brings additional improvement. Still work to do on pose and elimination. End of talk.
Question time. Don't be shy. Question time. Well, the first question that comes to my mind is like kind of obvious question is if the likelihood ratio is understood and is appreciated by judges in the real court.
There is
Since in these
yeah.
lectures we have learned that the likelihood ratio is our best friend.
Yeah.
So let's
Well, at least it's my best friend, and I want to share my friends with everyone. Well, there is a little problem here because judges and lawyers, the judges need to be aware of, so the lawyers need to be aware of this because they have to defend the cases. So they have to understand likelihood ratio as well. They probably studied law because they didn't like mathematics very much. So there is there is some missionary work to do, and we're working on that. That is one thing. Judges, same story. But nowadays in the Netherlands, in court cases, if, for instance, if we look at the Netherlands Forensic Institute, who are very much in favor of using this type of evidence quantification, they write, and what they will have to do anyway is write a very big report. So it's not just that they give a number, but they have to describe in detail how they made the comparison, and then they can also describe the meaning of the likelihood ratio. So it's a matter of correct reporting to help the judge understand. But still, it is in its infancy.
But the Netherlands Forensic Institute, is it governmental or kind of private institution?
It's governmental. Yeah. But they are supposed to be objective. So where the police has the task of finding possible suspects, they have to come up with an objective measurement. So this is clearly separated from the police. It's different per country. In the US, they're not very much in favor of likelihood ratios.
They just shoot and then they ask questions.
Yeah, and they still want to rely on experts, even though there are many cases where the expert had to be disqualified afterwards. But judges tend to, and juries tend to like to listen to experts who convincingly explain that this must be the culprit. So they're not very much in favor of this system. And of course there are a few drawbacks if you look at the likelihood ratio, because we need the probability densities. And how do you get probability densities if your data is complicated? So that is the hard side of it.
Another question?
Can you please come back to slide
29.
Yeah.
Must be this one.
So, as I know, one of the most famous algorithms for face recognition is analyzing the distance between the eyes, the nose, and the mouth, usually. Can we downsample all the area of the face except this for making our test.
Yeah, what you say is actually, with all due respect, wrong. This is how face recognition is usually sold in press, like measuring these distances. If you build a classifier, we did this as a very early, when we started to work on face recognition. In the very early days, we said, okay, what we will do is we'll determine eye coordinates, nose coordinates, mouth coordinates. We have those 4 points, and we will treat those as features. We will train a classifier on those features, and we do this in a relative way because you never have the number in centimeters. It's always in with respect to this interpupillar distance. If you build a classifier that works on that, what you get is equal error rates of 30–40%. So, although in press people like to say this is how it works because this is an easy way to explain to a larger audience how face recognition should work, it doesn't work like that. What is a very common method of working with face recognition is, oh, I should go, where was it? All the way in the beginning of my first talk, right? Yeah, this one. This kind of suggests this, right? But what this does is, this is a flexible network. It is overlaid on the face, so for you need an initial estimate of some reference points. And then, if this would be the other example, what this network does is automatically tries to find similar points, not looking at the distances, but looking at the texture. And this type of classifier uses that textual information. Also, it tries to use the distance. If you talk to the people from, well, it was devised in Bochum, and the company was called ZN, and later it was called, now it's Morpho actually, or the successor. If you talk to those people, they say these distances really don't matter much. The most important is the textual structure.
If I remember correctly, you mentioned that while using CNN, you extract features by using pre-trained network. Am I right?
Yeah, but it's not a pre-trained network on generic data. So this guest of ours, now my postdoc Dan, she pre-trained the network on these facial data sets.
This facial.
Yeah, this all facial. So, and you see some of them are pretty large, like there's 10,000 over here, 1,000 over there. So she took this data to train her network.
And you train all the system from these data sets and use that weights for your system?
Yeah, for
feature extraction?
For feature extraction only. So let me see. This is her network. She trained it as an identification network. And then what we did is, after training it as an identification network, we throw away the softmax layer, and we throw away the fully connected layers, and we use the layer before that for features, as a feature layer.
Okay, I understand.
Other questions?
I'll try it. I've just a simple question, and maybe it comes from not very experienced in this field. I was wondering if maybe we could train a feature extractor, like a single CNN, for example, with like different resolutions, so different level of downsampling of the images, as a sort of data augmentation procedure, and if that was in some sense comparable, at least, to the approach you presented.
Yeah. Simple questions could be good questions anyway. Also, the simplicity of the question never says anything about the length of the answer, but in this case, the answer can be short. This is what she did. That's why if I look at the, if you look at the, let's see, is there, yeah, the name of the network. Oh, let me see, where is it? Next one, yeah. Resolution invariant deep network. So that was her, this is what she devised in China. And you can see that actually what she did is, there are all kinds of interpupillar distances over here. High resolution as well as low resolution ones. And before training the network, she upscaled them all to the same resolution. But in a sense, she did what you suggested, to make the network somewhat invariant to resolution problems. So that was already part of it.
Sorry, another very simple question. I was wondering, I don't know if it can be applied because of the resolution of the images, but sometimes what I saw is that pre-training on like image data, for example, can yield actually better weights just because they are more stable. So like pre-training or even on a different task, for example, on
Yeah,
the image
true.
net. Do you think that could be helpful in this case, or just as a pre-training, let's say?
Could be, but I think the network that she designed is a pretty simple one, not too many layers. I think if you want to look at these networks, you should always wonder, but this is a hard question, how many layers do I actually need for my problem? If you take VGG with 19 layers or even more up to 100 layers, you need a lot of data, and then you'd better train with generic data. If you can tune your network to the problem that you're dealing with, I think you will always get better results if the training data is specific for the problem.
Thank you.
More questions?
Can you comment a little bit on the problem of face spoofing when you deal with face at a distance?
Yeah, I think face spoofing at a distance is at least a lot easier than face spoofing nearby, because it's hard to check whether you're wearing a mask or not, or so when you want to work at the distance, face spoofing is a bigger problem. Also, de-identification is easier if you don't want. The cases that we're looking at is we're trying to spot criminals in the crowd, more or less. If criminals are aware of that, they could wear a funny hat or a shawl or whatever to cover parts of their face, and then the problem would get harder and harder. So, yeah, spoofing or presentation attacks, either way, either to look like someone else or to not look like yourself, are easier. Yeah.
Okay, it doesn't fit with what we talked about, but I'm just wondering if you did some work on iris at a distance.
No, not at all. Not at all. And distances for iris at a distance are a bit different from distances that we're talking about here. So the one, yeah.
So
Yeah.
I was just wondering.
Yeah.
Any other questions? No? If not, let's thank you. Let me thank him once again for coming here and giving lectures. If we are lucky enough to be next year, we will do the same, with different talks maybe.
Hopefully, yes. Okay, so.
Some additional question. I just wonder if while using live training or CNN,